Welcome back to our lecture series on automated machine learning. We are still in the age of foundation models, and today we would like to talk about prior-fitted networks, PFNs, for hyperparameter optimization. So what was TAP PFN, which is where PFN also stands for prior-fitted networks? So more the idea was we do it once offline for many synthetic data sets. We can sample these from some kind of prior distributions, and then we train the PFN model on these kind of synthetic data sets, right? And then for a new real-world data set, we can obtain a distribution across all of the distribution on Y test, given X test and the data set. This was the training data set in one single forward pass. The nice thing is one can also think about PFNs in general as a surrogate model for Bayesian optimization. So the core idea is we replace a Gaussian process, GP, via empirical base with prior-fitted networks, PFNs. And then we can do direct in-context learning. So by using the PFN as a surrogate model and approximate the posterior predictive distribution in a single forward pass. The key idea, key shift here is that we don't need to fit the model parameters anymore. So for example, the GP length scales of our kernel to our history data, but we directly feeding in again everything into our foundation PFN model and using it only once in a forward pass from WAS for free, and then have inference is instantly available. That reduces then a lot of computational overhead, and at the same time, if we have fitted our PFN for BO well, then we have already a prior encoded in that, which hopefully helps us to directly go for better predictions. So how to learn that prior? So the objective is to train a transformer model to mimic Bayesian inference for a specific prior source. We're saying P of our data set. The process is we sample synthetic data sets, which is more historic information as always from the prior. That could be we using GPs and sample one GP from that and doing some optimization, or BNNs or HPO. There are different kind of priors actually we can leverage where people were more having a surrogate model which gives us already a possible landscape we'd like to optimize on, and from that we can simply generate a lot of history data. We split our training set arbitrarily in train and test queries. The nice thing about that is we don't really have to follow any kind of ordering, because although history data has an original order, we can also in principle violate that, because it doesn't matter whether I have that one point at the very beginning or later on. As long as I'm doing that uniformly, that should work out fine. And then we minimize cross entropy loss. So the approximation of a posterior predictive distribution was saying, okay, given the train and our test configuration, we would like to minimize cross entropy on that. Given our weights of our new network, of course. And the idea is we use a Riemann distribution to discretize buckets to model arbitrary potential multimodal posterior shapes with that. Then we can go one step further and say, okay, we'd like to learn or to predict learning curves. Learning curves was the idea, okay, we're training a network for a certain budget, for example, epochs. And we have seen that more here until here, here, here. So we only have seen these kind of points. We don't have seen the full curve, but only the points here on the plot. Of course, if you would know where it ends, it would be optimal. So we would like actually to figure out that that's the best one, and we should spend as much training budget onto that curve if we would like to maximize. FT-PFN is now doing more as the following. It tries to approximate which kind of bounds more or less that learning curve could go on. So that's here the dotted one is the mean point, and then we have the distribution more or less here for the blue curve where it could land at the very end. That helpfully gives us information what is the most promising configuration under that predictive distribution at the end. So we replace online surrogate training with a transformer-based PSN again and performs Bayesian inference via in-context learning and single proof plans. That's the same idea as before. We do meta training via syntactic priors, so more is also the same idea again. We only have to think about what it means to have syntactic learning curves, and what they proposed actually in 2024 was that if we would like to have a performance at CT at time point t for a given configuration lambda, it's more or less a weighted combination of certain basis function, which was proposed actually before already. So it could be power law or Hill or whatsoever. So there are different kind of basis function which say, okay, what is the shape more or less? It goes more like that or that, or some more linear trend or more exponential trend or whatsoever, right? And it could follow in principle everything. We have more these kind of weights which can be sampled. We have these kind of inputs to it, and then we have some kind of further parameters. So the variance of the normal distribution we would like to sample from, right? I showed you here this kind of distribution we have at the end. We have the final performance, we have the basis function and the weights. And all of these are sampled from a randomized neural network, which only gets as an input the configuration, has completely random weights, and should output us all of these parts for simulating more that learning curve. The only thing which is not sampled is C0 Morse. It's assumed to be independent of lambda. So where Morse the starting point of our learning curve is. I don't fully understand that from the paper, because obviously here C0 is not always the same, and depends also in their example on lambda. Of course, it depends a bit of what lambda is encoding. So if lambda is not encoding, for example, the initial sampling distribution, as an initial weight distribution of your neural network, then of course it should be always more or less at the same point, but might not be the case actually in practice. Then they also extended that to what they call IFBO. And here the idea is saying, if we have these different kind of learning curves, as I showed you here on that slide before, the question is which of these points you would like to continue, right? So would you like to invest one more epoch here or here or here? But the point is we're getting only one more epoch for all these different kind of learning curves, and then it's freezed again. And it's sort of more say, okay, we would like to continue again for one epoch or whatever kind of number of epochs you would like to have. But as always, training a little bit more one of these learning curves. The question is which to pick. That's the idea of freeze and SORBO. And they now, based on the PFN described on the previous slides, adding a special kind of acquisition function on top, which is a parameter-free acquisition that randomizes the horizon, and this serves at every step to hedge risks. And the idea is simply saying we have different kind of horizons. So say, okay, would I like to ask my PFN model to go really until the very end, so B max, or already stop earlier? So more is only doing one step and seeing then what performs best. So that's the horizon, how far we would like to look into the future with our learning curves. And in addition, saying we would like to have a threshold. So what do we expect, how much, do we get better than this threshold by doing that kind of horizon? And then more or less choosing that kind of configuration, that kind of learning curve we already have, which has the highest probability on getting better than our threshold, given that kind of how many more epochs I will invest in that specific learning curve. And that I extend then by, as I said before, a certain amount of, for example, epochs. That's the entire idea. combining more of these FT-PFN in context to get the posterior distribution. We sample then our horizon and our threshold parameters in each iteration, select them based on that acquisition function, best configuration, and then source or more unfreezing our learning curve for, let's say, one step, one epoch, whatsoever, or a bit more learning, and then updating everything we have seen now on that a little bit more trained learning curve. So with that, we are at the end of understanding how to leverage PFNs for learning curves. So in a multi-fidelity setting, you can say, we, as always, using PFNs pre-trained as a foundation model on BO-like data. Now we have to think about how to model these kind of synthetic learning curves, and then simply using a PFN as an efficient surrogate and having a special kind of acquisition function on top, which tries to trade off between long horizon goals and short horizon goals, and different kind of thresholds and being robust based on these kind of PFN models. With that, I hope you learned a new perspective on that and that we see us again in the next video.